All right, I just recorded the whole problem without audio, so now we're doing it again. This is Engineering 305, example problem 516, thin wall pressure vessel problem. A cylindrical pressure vessel with an inside diameter of 1.5 meters is constructed by wrapping 15 millimeter thick steel plate into a spiral, and butt welding the mating edges of the plate. Take a look at figure 533, which is right there. Determine the normal stresses. Determine the normal stresses, sigma n, perpendicular to the weld, and the shearing stresses parallel to the weld when the internal pressure in the vessel is 1500 kPa. So they've given us all of the information we're looking for. What's our pressure? 1500 kPa. I've got a radius equal to, right? Because you know the equations that I'm working towards is the axial stress is equal to PR over 2T. So I need to know what my radius is next. And I'll tell you what, the last time I recorded it without the audio, I put down that the radius is 1.5, but it very clearly states the diameter is 1.5. So the advantage of screwing it up is now I get it right. So it is 0.75 meters, right? Diameter over 2. And then lastly, it's how thick is it? Well, there we go. My thickness is equal to, I'm going to convert this over to meters so that I am in consistent units all the way across. I don't have to do any messing around in my equations. So now I've got my axial stress shown here on the figure, and that sigma A is equal to my x direction is equal to, trying to write a P and I PR over 2T is equal to 1500 kilopascals, PR 0.75 meters, divided by 2 times the thickness 0.015, or what I should have, maybe I could have done 15e to the negative 3, but that doesn't matter. You can start seeing the 0.015 cancels with the 15 there, and the reason for doing that is then because the kilopascals with an extra e to the 3 becomes a megapascals, and so that would have been 1,000. And then you got 0.75 divided by 2. It all works out. It all works out. This is 37.5 megapascals. And if you know sigma A, well, that's equal to sigma H over 2, which is equal to sigma Y, right? I'm going to go to green, and that's this. Whew, didn't like that. That's this. That hoop stress is in the Y direction at this point. So if I just multiply that by 2, that's going to give me 75 megapascals, because that equation would have been PR over T, and I don't need to do that twice. So I'm good. I'm good with that. I got my two answers now. And there's, because of the way I wrote them, maybe there's not a great way to put a box, but there's sigma Y, and that's sigma X. And then we had to do this stress transformation to get us to the right angle. And they told us, and here's this sentence: the butt welded seam forms a 30-degree angle with the transverse plane through the cylinder. Okay, so something here is 30 degrees. Well, if I drew that, If I drew that, and now if I had to guess, I would say, well, that looks more like 30 degrees. But, and this is, that could be my transverse plane. It forms an angle of 30 degrees. I would have assumed that was positive, but that's the 30 going down, not 30 going up. So, but then I'll go one more for you, and that is the problem actually has an image where they drew for us this little sketch, and they said, here's my X, here's my Y, here's my N, and they labeled this as minus 30, and here's my T. So now all I have to do is do a stress transformation. So sigma N is equal to sigma X cosine squared theta plus sigma Y sine squared theta plus shear XY. Well, I can write sine theta cosine theta, but I know that's 0. We don't have any shear stress. So it's just going to rely on those first two terms. So I can punch that in and calculate that. Because, I would say sigma X is equal to 37.5 and sigma Y is equal to 75 megapascals. And theta is equal to minus 30. And just punch that into a calculator. Or I could not. I could skip that. And I could just say, we've got this tool called Aimsweb. And if I punch in the values, 37.5 in the X and 75 in the Y and 0 shearing stress and a negative 30-degree angle, and I hit calculate, I just have to be over here. And then it gives me the values. It gives me the stress in the X direction as 46.9. The stress in the N direction, sorry, is 46.9. I can't draw on this screen, but 46.9. And I get a shear stress of 16.2. So actually, since I told you I'd already recorded this one, I did it. Oh, that's not the button I want. I want that button. It's actually right there. I cut and pasted it in. So there's my answer. Here's sigma n is equal to, and tau nt is equal to those numbers there, and that matches up exactly with, well, almost exactly with what's in the book. In the book, they went minus 16.24 MPa. They carried one extra significant figure, and I think that's significant. One, we made this huge assumption that this is a thin plate, and then when our radius was 0.75, we neglected the fact that we could have added another 0.015 and used the outside radius instead of the inside radius. There's nothing that says the inside radius is the right answer, the right value to use. We could have even averaged the two of them and said, I don't know if it's the inside or the outside. Let's choose something in the middle. All of those are valid approaches, and that makes this problem even more interesting in that now we're clearly into a world where there just isn't one answer. That if we assume inside radius, we get one thing. If we assume outside radius, we assume another thing. Honestly, when we put this, we didn't. There's an assumption here. Assume inside radius. And why am I assuming inside radius? Because that's the value they gave us. I didn't have to do any calculations. I didn't have to add anything. But that's not any better an assumption than the outside radius. The key is that this system says it's thin. And if it's thin, then the radius on the inside is the radius on the outside, and those answers are just as good as each other. What we'll find is that both of those have errors and give us different values than if we use the thick wall pressure equations, which are more accurate, but they give us a different answer. And you're going to see they're a pain in the neck to use. That's why these are beautiful. These are really easy to use, but they have their limitations. And so we need to just be aware of those as we move forward. So our next section is going to be about thick wall pressure vessels. And so you'll get to kind of experience what the difference is in the length, the size, the demands of the calculation. But then also, we do have the opportunity then to start looking at what's the accuracy, or how close do these three equations, whether we use thin wall inside, thin wall outside, or whether we use thick wall, how close are those approximations to each other, and what do we want to look at? So, hope you're doing well. More to come.